welcome to CEC-UGC lecture series. I'm Neeti Bhutani from Hindu College, University of Delhi, and you're watching the 13th lecture in the series Mathematical Methods for Economics. In today's lecture, we will continue to talk about functions as we have been doing in the last couple of lectures. So far, the specific functions that we have covered are linear functions, quadratic functions, and cubic functions. In today's lecture and the next, and maybe the one after that as well, we will cover two new classes of functions, namely power functions and exponential functions. And the key takeaways from today's lecture are going to be: I will start by talking about the properties of powers or exponents as they are called. I will talk about the fundamental power rules that govern both power functions and exponential functions. I will then go on to define power functions and also explain the difference between power functions and exponential functions. The two themes for this particular lecture, there are two themes around which my discussion is going to revolve, and the two themes are the first one being the domain of power functions, and this is something you must pay attention to, and the second one is the graphs of power functions. But before we start talking about power functions, I will first go back to basic principles and talk a little bit about powers or exponents as they are called. I'm sure you've all studied powers in school, and this is something you would know quite well, but nevertheless, let's have a quick discussion on powers or exponents, because I just want to ensure that we are all on the same page, and also because this is a discussion, this part of the discussion will guide our discussion later on in the lecture when we discuss the domain of power functions. Okay, so let's get started with powers here. Look at this expression here on this slide. If we consider the expression a to the power r, where a number a is raised to the power r, then a is called the base and r here is called the exponent in this expression. Now this expression a to the power r, it lends itself to specific interpretations depending on what a is and depending on what r is, depending on the value that a takes and depending on the value that r takes. In particular, and this is a rule that you would have done in school, if a is any number and r is any natural number, which is to say that r is your positive integers 1, 2, 3, 4 and so on, then the expression a to the power r is defined as the number a multiplied by itself r times. Okay, so the expression a to the power r is the number a which is multiplied by itself r times. Another way of looking at this rule is that if we allow r to be any natural number, any positive integer, then the expression a to the power r is defined for any number a. So let us take an example to see what exactly here the calculation means. Suppose a is equal to 2, our base here is 2, and r is equal to 5, then we have the expression 2 to the power 5, which is nothing but 2 multiplied by itself 5 times, and that, as you can calculate here, 2 times 2 is 4, 4 2s are 8, 8 2s are 16, and 16 2s are 32. So in this way, we can talk about powers which are positive integers for the expression a to the power r. Further, suppose r is equal to 0. Now, if r is equal to 0, then in the expression a to the power r, we'll have a to the power 0, and this in turn is equal to 1 as long as a is not equal to 0. We have to place the restriction here that a is not equal to 0, because if a is equal to 0, what will happen? If a is equal to 0, then we will get 0 to the power 0 which is not defined. So we for a power which is 0 in the expression a to the power r, we will take all numbers a except a not equal to 0. Now, to summarize the discussion so far, we have looked at positive integers as powers. That was the first rule that I just mentioned, and we've looked at 0 as a power. Now, the question is, what happens when we have negative integers as exponents? Because very often you see numbers with negative exponents. So we have talked about 2 to the power 5. The question is, what is 2 to the power minus 5? So to allow for negative integers as powers, let us suppose let's put r equal to minus n, where n is again any natural number, 1, 2, 3, 4 and so on. So here our expression a to the power r becomes a to the power minus n, which is then equal to the reciprocal of a to the power n. Now note here, again we're going to place the restriction that a is not equal to 0, because again if a is equal to 0, what we'll end up with is a 0 in the denominator here. We'll have 1 divided by 0, and as we all know that division by 0 is not defined. Let's look at an example to illustrate an exponent which is a negative integer. So for example, if I take a equal to 2 and I take n equal to 5, then my r becomes, because I've taken r to be minus n, then r becomes minus 5, so that my expression a to the power r becomes 2 to the power minus 5, which is 1 upon 2 to the power 5, and that is nothing but 1 divided by 32. Okay, so till now we have looked at exponents. Let me just summarize this. So we have looked at exponents which are integers. So we've looked at positive integers, we've looked at negative integers, we've looked at 0 as a power. The question now is, can we extend our interpretation? Can we examine this expression a to the power r when the exponent is any fraction, when the exponent is a rational number? And for that, we will look at some fundamental power rules, or the properties of exponents, or the laws of exponents as they are called. So the question here is, can we examine the expression a to the power r when we have rational numbers as exponents? The point here is, we have already looked as integers as exponents. Now you can argue here that integers are also rational numbers. Yes, integers are also rational numbers, but then the set of rational numbers is a larger set. So we want to see if we can generalize if we can generalize things and examine the expression a to the power r for rational numbers, and for that matter even for irrational numbers. Now to do this, I will digress a little bit, and let me introduce, actually this is something you would already know. Let me bring in the fundamental power rules that govern power functions and exponential functions. The first rule here is that if I take two expressions a to the power r and a to the power s with the same base a, then if I want to multiply these two expressions, then a to the power r times a to the power s is nothing but that same common base a to the power of r plus s, where I simply add up the two powers r and s. So a to the power r times a to the power s is equal to a to the power r plus s. Let me just point out here, because this is something which is very important for this particular rule and also for the next couple of rules that I'm going to talk about. We are going to take these rules as applying to all these, I should say these rules apply to all real numbers r and s, and here we're going to take a, the base, to be positive. So now you might ask, why are we taking, if you look at the statement on the top, I'm defining these rules for a greater than 0 and all real numbers r and s. Okay, so these rules, they apply to all real numbers r and s, and here we are assuming that a is positive. So to explain why I'm taking a to be positive, you have to understand that here I am taking all real numbers r and s. Now, because I am taking all real numbers R and S, I might be in a situation where these exponents R or S might be numbers like half. So if, let's say, R here, please see where my cursor is. So if R here in this expression a to the power R is, let's say, a number like half, okay, then what will happen? We are basically, it means that we are taking the square root of a here. If we are looking at a to the power half, we are taking the square root of a. And as you all know, we've covered this in the previous lectures, we can't take the square root of a negative number. Now similarly, let's suppose R is equal to 0 or S is equal to 0, then clearly in this case you can't have A equal to 0 because 0 to the power 0 will not be defined. So to rule out these situations where where you don't want to include negative values of A or 0 value of A for the base, we take A to be positive. But so everyone, please note here, you would be thinking here that we do take powers, we do calculate exponents where the base is negative. So note here that A can be negative also. So for specific values, if we take specific subsets of R and S in the real number on the real number line, then we can allow A to be a larger set of numbers. Also, we can allow A to be negative also or 0 also, but that depends on the specific values that we take for R and S. But clearly, if we are in a situation where R is half or R is 0, we can't take A to be negative. So that is why I have taken A to be positive. Yes, we will look at cases where A is negative also, and we take a larger set of numbers in the for the interval to which A can belong, and we'll look at those cases also. And actually, go back to the first rule that I gave you. The first rule said that if R is any natural number, so if you take R to be a positive integer, R is any natural number, then you can allow A to be any number. So there you are, we have already relaxed A greater than 0. But yes, if we are taking R and S to be all real numbers, then we have to restrict ourselves to A positive, otherwise we'll mess things up. Okay, so that was a comment that I wanted to make, and I hope you've understood it. This is quite important here. In case you still haven't, you can either replay this video, this part of the video, or I will be revisiting this part when we talk about power functions, because this will come up again when we talk about power functions. Okay, so our rule 1 was that A to the power R times A to the power S. If we multiply these two expressions, we get A to the power R plus S. Okay, what does the second rule say? The second rule says that if we were to raise A to the power R to the power S, so if we were to raise A to the power R to the power S, that's nothing but A to the power R times S. So you simply have to multiply these exponents R and S, right? So if A to the power R is raised to the power S, that is A to the power R times S. The third rule says that, again we are note here that this is for A greater than 0 and all real numbers R and S. The third rule says that A to the power R divided by A to the power S, and in fact these are rules that follow from your regular properties of powers. So A to the power R divided by A to the power S is equal to A to the power R minus S. And then rule 4, and we'll just talk, I'll just show you some examples to illustrate these rules so that you are comfortable with these rules. Rule 4 says that if I were to raise A times B to the rth power, so A times B to the power R is A to the power R times B to the power R. And finally, the fifth rule is that if I take the rth power of A divided by B, then that is A to the power R divided by B to the power R. Okay, so let's see how these rules work. Let's look at rule 1, which was A to the power R times A to the power S is equal to A to the power R plus S. Let's see why this rule, let us try and understand why this rule works. So for example, if I were to take R equal to 2, and s equal to 3, then a to the power 2 is a squared, so that's nothing but a multiplied by itself twice. A to the power 3 is a multiplied by itself 3 times, and that then gives us a multiplied, the number a multiplied by itself 5 times, which is a to the power 5. Similarly, I could even have negative integers as exponents in some parts here. So for example, if r is equal to minus 3 and s is equal to 2, we have already shown that a to the power minus 3 is nothing but 1 upon a to the power 3. So that then becomes a squared divided by a cubed, and this you can see here. So this then becomes a times a divided by a multiplied by itself 3 times. 2 of the a's will get cancelled in both the numerator and the denominator, and we get 1 divided by a, which is a to the power minus 1. And you can see here clearly that this conforms to our r plus s. R here is minus 3 and s is 2. So r plus s is minus 1. So clearly the rule works. Let's look at the second rule now. This is saying that a to the power r, the whole thing to the power s, is a to the power r times s. Let's take an example to see how this rule works. Again, if I take r to be equal to 2 and s to be equal to 3, so this is saying I would want to take the third power of a square. So that is nothing but a squared multiplied by itself 3 times. So a squared times a squared times a squared. Now what is that? A squared is nothing but a times a, and if you multiply a times a with a times a and the third time with a times a, that gives you a to the power 6. And clearly that conforms to our rule that a squared, the whole cube, will be nothing but a to the power 2 multiplied by 3. So 2 multiplied by 3, r multiplied by s here is 6. The third rule here says that a to the power r divided by a to the power s is equal to a to the power r minus s, and that is natural because we have said that 1 upon a to the power s is nothing but a to the power minus s. So if I write this as a, if I write the left hand side as a to the power r times a to the power minus s, this then becomes a to the power r minus s. Again, let's look at an example to see how this works. So here I have taken r equal to 5 and s equal to 2. So we get in the numerator a to the power 5, which is a multiplied by itself 5 times. In the denominator we have a squared, and you can see here that 2 of the a's in both the numerator and denominator get cancelled, and you get a cubed, which is nothing but a to the power 5 minus 2. Rule 4. Rule 4 says take the product of AB, the numbers AB, raise that to the power r, and that is equal to a to the power r. So you can open up the brackets and take and raise both a and b individually to the power r and multiply these two expressions. So a times b to the power r is a to the power r times b to the power r. Again, let's look at an example. Here we have r as 4. So if I take a times b to the power 4, this is to say that a times b is multiplied by itself 4 times. So if I do that, I can then collect all the numbers a, so that will be 4 times, and again the number b will also appear 4 times, and that gives us a to the power 4 times b to the power 4. I hope this is making sense. Okay, and the final rule is that a divided by b to the power r is equal to a to the power r divided by b to the power r. So again, you just open up the brackets and raise both the numerator and denominator to the power r. Let's look at an example with both positive and negative exponents. So if we take a divided by b to the power 3, That is, if we understand it the way we do in the usual interpretation, that's a divided by b multiplied by itself 3 times. So a divided by b times a by b times a by b, which is nothing but a cubed by b cubed. Okay, so that's conforming to our definition. And let's take another example where I have taken a as 4, b as 5, and I have raised this fraction to minus 2. Okay, so that then becomes 4 to the power minus 2 divided by 5 to the power minus 2. Basically, you can take it as 1 divided by 4 by 5 the whole squared, and that way also it can work, or 4 to the power minus 2 divided by 5 to the power minus 2. So that is equal to 5 squared divided by 4 squared, and that's 25 by 16. Here I'm just directly applying the property, and that then gives me 25 by 16. I've just taken 5 to the power minus 2 to the numerator to get 25 in the numerator, and 16 goes in the denominator. Okay, so that's as far as the general properties, the fundamental rules of exponents are concerned. Now, we are in a position to now discuss exponents that are fractions, exponents that are rational numbers. So let's see how we can examine the expression a to the power r for an exponent that is a rational number or a fraction. So let's assume here that we have a number p, which is an integer, and we have q, which is a natural number. Then our rule says, this is the rule for fractional powers, that if I were to raise a to the power p by q, and you can see here p by q will be a fraction here because p is an integer, q we are not allowing to be 0 or negative, right? We are taking q to be a natural number. Basically, q should not be 0 here because we have p by q. So by definition, and we are just going to prove this property, by definition we have a to the power p by q is equal to, now there are two ways in which you can calculate a to the power p by q. One is that you can first take the qth root of a and then raise the whole thing, the result that you get for the qth root of a, to the power p. So that is one way of looking at things. Another way of looking at things is that you can actually first raise a to the power p, and then for the result that you get for a to the power p, take the qth root. So take the qth root of a to the power p. Both ways of calculating a to the power p by q give you the same answer. And here again, note here that we are maintaining our restriction that a is greater than 0. We will have situations, and I'll just tell you the restrictions on p by q, where you could have a negative, but just hold on to that. Let's first prove this particular property, that a to the power p by q can, which can be written as any one of these two expressions here on the right. Okay, so let's see how that works. Let's look at our rule 2, the fundamental rule of powers, the second rule, which is saying that a to the power r, the whole thing to the power s, is equal to a to the power r times s. In this particular rule, let's take r, this particular power r, as 1 by q, where q is a natural number, and let's take s as the integer p. Okay, so then I get a to the power 1 by q, the whole thing to the power p. I've just substituted for r and s, and by rule 2, what do I have on the right hand side? That's a to the power r times s. So I get a to the power 1 by q times p, which is our expression on the left hand side, which is a to the power p by q in the definition. Okay, so this is something that is something that you should note, and this actually gives us a very useful, a very easy way to calculate expressions with fractional powers.